Okay, so I have this optimization problem. It says an open top box is to be made by cutting small congruent squares from the corners of a 12 by 12. So I have this 12 by 12 sheet of 10. So in other words, that's 12 inches. And this is 12 inches. Pretend I can draw to scale. And then it talks about bending up these sides. So what's happening here is we're cutting out these corners and then we're going to bend them up. So that's what you're seeing for the actual sides. And we want to know the max volume, okay, once you get all these sides built up, this max volume. Now, we need to look at, before we start plugging things in, each one of these, we don't know what their value are, and they're going to be the same because it said squares. And so this is what we're trying to maximize. And so hopefully you can see that this has changed now from 12 to 12 minus 2x. Oops, I went a little farther. To right there. And the same here, 12 minus 2x, because these are sides now, okay, that they're being folded up, all right? And from here, I remember, well, if this is going to be a max, and it's the volume, that's going to be what, the height times the length times the width? Kind of, sort of, remember that? And remembering, then it looks like the height, in this case, when you fold these up, would be x. The length and the width are the same, 12 minus 2x and 12 minus 2x. Multiplying this out, so I FOIL the 12 minus 2x times 12 minus 2x, and then don't forget about that x on the outside. Okay, so that's how I'm getting 144x. And then minus 48x squared plus 4x cubed. Now, to find a max, remember, that's just finding the critical point. So I find the first derivative, which would be 144 minus 2 times 48, 96x, subtract 1 from the exponent, just using power rule. And then plus 12x squared. And to find the critical point, we set this equal to 0, and I'm just going to rewrite this in order of the highest exponents. Plus 144. And kind of sort of home free is I remember that each one of these I could divide out of 12. Just might make it a little bit easier when I have to actually factor. So I have 0 equals, bring the 12 out front. That leaves me with x squared minus 8x plus 12. And so this is the piece I'm going to factor. X and x, two values that you multiply to get 12, 6 and 2. And it has to be negative and a negative, positive 12, and then that value. So I get either x equals 2 or x equals 6. Now, one thing you want to kind of go back and look at is, what is the domain? And why do we care? Why is that important? Well, if you plug in x equals 6, then you don't have a side, right? And so we would write the domain in this case would look like this. And how do we know which one of these, how do we know what these values are? Well, go back to your original function up here and plug in 2, and then plug in this case, both endpoints. Remember, when you have endpoints, a closed interval, a closed domain, this is closed, you plug in those endpoints, and when I plug these into my calculator, I got 128, I got 0 and 0. Another thing that's kind of important to see is what does this even look like as far as a graph? So this is my volume function, which was what, 144x minus 48x squared plus 4x cubed. And we said that the domain was going to be between 0 and 6. And we already know from our answer that the y value is way up here at 128. So I just changed it to that. And now we can see why certainly that's a max and why these values are 0. Okay, so it just kind of helps you see the actual graph. So the maximum volume in this case would be 128 cubic inches. Okay, you have 3 x's in there. And then each cut out square would be 2 inches because that's what we got for our value of x. So each square, 2 inches, and then our maximum volume, 128 inches cubed.